Have you ever noticed how high-end audio systems, high-end sound systems, often have a little graph somewhere on the system with bars that move up and down as the music's playing? Well, these bars are actually representing the sound that's going through the system and being played out your speakers, and it tells us something about the sound. It tells us about the frequencies in the particular sound. For example, if there are low notes, those show up as low frequencies, and the height of the bar represents the loudness of those notes. Similarly, high frequencies show up over here on the right-hand side. Now, this is useful because if something goes wrong, for example, or perhaps there's feedback in the system, one of the bars may jump up high and tell us the frequency where the feedback is coming from. Well, we can take this frequency analyzer, the spectrum analyzer concept, into our world of surface texture. If we have surfaces, we essentially have a song that's being played. Our song may have low notes in it. That's the general trend with long wavelengths. And we have high notes in our surface, the fuzziness or the roughness of the surface being torn or machined, and these are very fine spacings or very fine short wavelengths. So in our world of surfaces, instead of looking at frequencies, we're going to look at wavelengths because we can actually see wavelengths by looking at the graph. And wavelengths are represented with the Greek letter lambda, and a wavelength again would be the spacing between the peaks, for example, of a sine wave. So instead of bars that represent music, we can make bars that represent how tall each of these sounds or shapes are in our surface. So this surface has some rather tall humps in it, so that would be a rather tall bar at the long wavelength side of our graph. The fuzziness over here we can see is not quite as tall as the lumpiness. The fuzziness, perhaps the fine detailed roughness, represents short wavelengths, and it also has a bit shorter amplitude. The height of the bar we call amplitude. And amplitude is the height of a sine wave at that particular frequency. So this height from 0 upward we call amplitude, and amplitude is the height of the bar over here that's being plotted. So we can make a graph that shows the amount of each wavelength in our surface texture when we're trying to analyze a surface, perhaps to figure out what's going on in our manufacturing process, or perhaps something related to the function of the surface that depends on wavelengths. So let's look at a rather messy surface right now, and this rather messy surface can be plotted as a wavelength content graph. There's math that converts this surface into its wavelengths. It's called a Fourier transform for you math nerds. And this Fourier transform output is the wavelength content graph in the case of surface texture. So hiding inside this surface, we can see fine details that are wiggling up and down that look kind of like these, and they're relatively short, so the bar would be relatively short. Now, also hiding in this surface are some longer wavelength humps and lumps. These longer wavelength shapes in this case are a little bit taller, and they might live over here on the graph. And then in general, there's a overall trend that's kind of a U shape running through this surface, and that general trend would be way over here at the long wavelengths, and in this case that trend is very tall, so the amplitude in the graph is very tall. This is a great breakdown of the surface because this might be the cutting action of the machine, this might be vibration, this might be straightness, or in application this might be related to oil retention or how we can glue to the surface, adhesiveness for example, and this might be chatter in a bearing, or this might be clamp loading as we're trying to squeeze two surfaces together. Now, in actuality, we don't get nice discrete bars. We might actually get a graph that looks like this. It's going to be a continuous graph that might have some spikes along the way. So don't expect to see clean bars when you measure your surface, but look for spikes in the graph. Those graphical features are very interesting when we start to talk about roughness and waviness and form, perhaps, because we can take these filters from our gauge and apply those to the graph also. We might have a case where we've set up our filtering to capture this zone over here as roughness. And we might have another zone we've established over here as waviness. And in some cases, we go even further and have a zone called form. So the wavelength content graph is a fantastic way of telling us what song is being played by our surface in terms of short wavelengths and long wavelengths. And we can even overlay our filtering conditions to see if our settings are extracting them correctly. So check out the Wavelength Content Graph if you're interested in exploring your surfaces deeper. And as always, you can reach out to us at digitalmetrology.com with any questions you may have. We love talking about this stuff.